Hello, it's me, Maria Sandoval, and today I will be talking about the chemical reactions. We're going over chapter 4. So I'm going to be starting off with the electron distribution in molecules of H2 and H2O. So starting here, you'll see that the electron charge distribution in H2 is symmetrical. So the way that you can tell that is that both of them line up here and they're on opposite sides here. This is your positive and this is your negative, and they're equally balanced on the molecule. Here in B, you can see that the electron charge distribution in H2O, water, is asymmetrical, and that's because you have all your electron charge up here and all your positive proton charges down here, which kind of makes it a bit lopsided because everything's up here for positive and everything's down here or for the negative, and everything's down here for the positive. So this is zooming in on the H2O molecule, and so each bond in H2O is actually polar, which makes the whole H2O molecule polar. And here we're looking at an ionic compound dissolving in water. So here you can see this is our water molecule, and it basically goes in and it rips each of these pieces of the molecule away from the original molecular form. So here you have just the tan negative charge, and here you just have the brown positive charge, which makes it quite easy for like ionic compounds to just dissolve in water, because that's kind of like its bang zone. It loves to do that. Just waiting for my slide. Okay, so water as a solvent. As we said previously, water is a polar molecule since it has the uneven electron distribution. All of the negatives up here and all the positives down here. It also has a bent molecular shape, which is why it was like kind of like a triangle, kind of, but it didn't have the bottom. And then another point to remember about water as a solvent is that water readily dissolves a variety of substance. Like I said, it's kind of its bang zone. It loves to just dissolve things. And water interacts strongly with its solids and often plays an active role in aqueous equations, which its favorite thing to do is rip things apart, so it would make sense. So here we're looking at the electrical conductivity of ionic solutions, and in this first one you see that the distilled water does not conduct a current, and that you just have your H2O molecules. You don't have positive or negative charges really showing yet. Here we have positive and negative ions fixed in a solid, and they do not conduct a current because they're too tightly packed. They can't move around and energize. So here we see our electrodes, the positive and the negatives. They're showing up. It's not like in the previous slide where they're all tied together. They can't really move. They have room to move around in the water. So here in a solution, positive and negative ions move and they're able to conduct a current. Moving on to writing equations for aqueous ionic reactions, the molecular equation shows all reactants and products as if they were intact, undissociated compounds. This gives the least information about the species in the solution. So we have silver nitrate and sodium chromate, and they give us this solid and an aqueous. So you can see there's a solid down here, and there we have our aqueous solution. We started off with 2 aqueous solutions though, so we've made a solid out of this reaction, which I'm pretty sure we go over later. There's like precipitation reactions that happen like this. So when solutions of silver nitrate and sodium chromate mix, a brick-red precipitation reaction, I was correct, of silver chromate forms. So we have a reaction going on here. So the total ionic equation shows all soluble ionic substances dissociated into the ions. This gives the most accurate information about what species is in the solution. So now we see we have our charges. So now it's not just the molecular equation. We have the negative and positive charges showing up for our solutions. Spectator ions are ions that are not involved in the actual chemical change. Spectator ions appear unchanged on both sides of the total equation. So here you can see the 2Na plus stays 2Na plus. 2NO3 negative stays 2NO3 negative. They don't really do anything. They kind of just watch. That's why they're called spectator ions. They don't do anything in the reaction. They stay the same on either side. So the net ionic equation's whole deal is that it gets rid of that. It gets it down to the base. It eliminates the spectator ions and only shows the actual chemical change that happened. So this is showing us how, like, this is where our spectator ions would be. This is the NO3 that we were talking about earlier, and this is the Na plus. And so you see they just sit there while the whole reaction happens. Nothing really happens. They don't change before or after the equation. So an aqueous ionic reaction in the three types of equations. Let me just make sure, because I think that that's what we'll be moving on to next. Yes, actually I went one slide ahead, so you have a bit of a head start on the next one, but we should have stopped at our total ionic equation. So that's all for this video, but on the next one we will be moving on. You have a little bit of a head start for that one. Have a good day. Bye. I hope you learned a lot, because I did too.